I will move to introduce our next speaker, Bob Sinkovitz from San Diego Supercomputing Center. He will be talking about optimization of text processing for the Wordflare knowledge graph. Bob, I'll turn it over to you.
Great, thanks Jay, and thanks also to the ECSS organizers for the invitation. So I'm going to be talking about a project that I finished about a year ago. And in advance, if anybody needs to email me, I didn't put this on the slide, but it's my last name without the final S at sdsc.edu, San Diego Supercomputer Center.edu. Okay, so this is a project. There we go. So the Wordflare project, this is pretty neat. It was something outside of what we typically do. We considered a non-traditional supercomputing application. It was really focused on the text processing. So the goal of the Wordflare project was to develop a tablet-based app to allow users to explore language and knowledge. And essentially, they were looking for relationships between words, what words that appeared close to each other in the text, or that would appear, say, in the same topic in a body of text. So the app it makes use of a very massive thesaurus, features dynamic visualizations of word relationships, and a small fraction of the content is human curated. So they note here about 9%, but the majority, the other 91%, is derived using computational methods executed on Exceed resources. So my part of the project focused on two very specific tasks. The first was to optimize the performance of the latent Dirichlet allocation algorithm. And I'm not going to go into the details of the LDA, but essentially it's one of the workhorses of computational linguistics. It's used for discovering topics or themes in a body of text. And then I also developed. Well, it started off with optimizing the existing software, but then I kind of started from scratch and took a new approach to develop a fast method to do a simultaneous search for a large number of words in a body of text. And I'll go into that in detail in the second part of the talk. Okay, so and I didn't put the math on here for it to be understood. I'll mention that in just a minute. So there are many implementations of the LDA algorithm, and the organization that I worked with, idea.org, they're a nonprofit based in Maryland who is working on this Wordflare app. They were using an implementation called Gibbs LDA++. This is a fast C++ version developed by, and excuse pronunciation, Zhuan Hu Fan and Cam Tu Nguyen. I believe they're at the University of Hanoi. So I put a little bit of math on here. I started looking at the math in the beginning, and as you might guess, immediately got bogged down. Fortunately for this project, I was able to ignore this very impenetrable looking math and just focus on the software. So when I did a profiling of the code, sometimes you profile a code and you get a very flat profile. You see, 3% is spent here, 2% of the time is spent somewhere else. This was the complete opposite of this. It was beautiful. I profiled it, and it showed that virtually all of the time was spent in a single method in the C++ code. The method is model sampling. And not only that, it was repeatedly called within a pair of nested loops. So you can see in this little snippet of code that we have an outer loop over index M, we have an inner loop over index N, and then we'll make the call to the sampling method. It returns a single integer, which is then stored in a two-dimensional array. And of course, what jumped out at me here is that this method is being called n times in a row with the same value of M. So it made me think that there may be some opportunity for reuse, for pre-calculating results and using them multiple times. And it turned out that there in further investigation of the code, that there was some good opportunity there. So as I just mentioned, the sampling method is called repeatedly with the same value of m. And we also noticed that within the code, only a few elements of these arrays that I've highlighted in red, the two-dimensional array ND, and then the 1D arrays NW sum and ND sum, are updated. In addition, they're only temporarily updated. So we're looking in this loop. You can see in the middle of the code block, I have a little note that says potential invariant, and I have some text that I highlighted in blue. So some things might jump out at you as potentially being invariant. It wasn't quite as simple as I would have hoped, because again, there are elements of the arrays that go into this expression that are being that are being updated. But if you'll notice, if you see the code that's highlighted in red, it depends on the index m and also on another index that we calculate called topic. It's only a single element of that array that's in fact being updated from call to call of the sampling method. So what we're able to do is modify the calling sequence a little bit. That's the block of text in the upper right. We pre-calculated this, what I'm going to call an almost invariant, this new array F1. We calculate that before we go into the inner loop over the index n, and then within the sampling method, we just update that single element of F1 that I highlight in red. We use it in the calculation, and then we do the update again at the end of the code. I should mention that there's some intervening code that I'm not showing here between this calculation of the array in the loop over k and the updating the element. So we really do need to pre-calculate invariant and keep track of modification, back them out at the end of the loop. So when we did this, we were able to get the entire application running about 1.5 to a little over 2 times faster. And this is going to depend on the number of topics that you're searching for. But overall, I think this was a pretty exciting result, especially since the LDA algorithm is used so heavily in computational linguistics. Okay, so then moving on to the next part of the project, and this is where the folks from idea.org were really using the majority of their compute time. And what they needed to do was identify words that are commonly found together. So the Google Books project solves part of this problem. If you're not familiar with Google Books, they take just massive amounts of text that they'll digest it and break it down into words, and then they'll look for pairs of words, triplets of words, quartets of words, and so on, and calculate the frequency with which each of those pairs, triplets, and so on occurs, and they'll do this as a function of time. So I give an example here, looking at the occurrence of 4 word pairs: beautiful woman, handsome man, handsome woman, and beautiful man. And as you would expect, beautiful woman and handsome man occurred pretty frequently, but we also see instances of handsome woman and beautiful man. So with the n-gram data, it's very easy to identify these kind of relations. But what the idea.org folks wanted to do was go a little bit further. So Google, what Google can't tell us through the Google Books and the n-gram project is how often a given word is preceded by other words. So in other words, it's very easy to learn that handsome is followed frequently by man, but it's very hard to find out which words frequently precede man. And if you ever look at the n-gram data, it's organized alphabetically by the first word in that doublet, triplet, and so on. So what we really need to do is search through all of those records, and we want to know all of the records that contain a particular word. And we don't want to do this just for 1 word or 2 words or a handful of words. we want to do this for large numbers on the order of 100,000 to 1 million words. So the way the problem was originally approached, and this is the way that the justification was written for the extract allocation, was essentially they did some benchmarking using grep, grepping through one word at a time, and then scaled up to the number of words that they would need to search for. So this really isn't a bad approach, but I'll show you in the next few slides that it's not a particularly scalable approach. So if we do, and it's the obvious way to go. If I was going to search for words, I would have a loop over the words that I'm searching, and I would execute grep for each of them. So imagine that I have this small document. It contains 10 lines. I have them labeled R0, R1 through R9. The R0 through R9 is not actually part of the document. That's just a record label. And that each of these lines, it's very simple. It contains 5 3-letter words. For example, the first line contains ant, boy, XXX, dog, XXX. Next line, XXX, boy, XXX, XXX, egg, and so on and so on. And what I want to do is process this file, and I want to write out new files that contain all of the records that contain a given word. So, for example, I want to find all of the records that contain the word ant. So I could execute a grep. I could search for ant bounded by white space, and then I'll get these 4 lines: R0, R4, R5, and R8 that all contain the word ant. But then I want to find all of the records that contain the word boy, and again I could do another grep. I could grep for boy bounded by white space, and I'll get these 4 records. And then finally, I'm searching for the records that contain the word car. And in this case, we get records R2, R3, R4, and R6. So very, very straightforward, very, very easy to understand. And again, not a bad way to approach a problem, especially since grep has been so highly tuned by many developers over the years. But the problem, though, is if you think about how this scales, it's going to scale with the number of words that we're searching for. So think of it when we're running grep. If we break it down, if we look at the analysis that's being done, the first thing I'm going to do is I'm going to read line R0. I'm going to search for a particular word. I'm going to read line R1. I'm going to search for a particular word, and so on and so on. I'm going to do that for all of the lines in the record. Then I'm going to execute my next grep. I'm going to be going back to the beginning. I'm going to be searching the 0th line for the word boy, the 1st line for the word boy, and so on and so on. So you can see that I'm going to be doing a lot of I/O. I'm going to be going through each record. I'm going to be going through the entire file one time for each word that I'm searching for. So it would be really nice if we could find a way that we could read in that line, parse it once, and do everything that we need to do on it. So I decided to create a new approach instead using hashes. So when we search for a large number of words in a document, as I mentioned, it's better to read each line once, search for all the words in one fell swoop. So in very high-level pseudocode, what I do is first I read the list of words, the vocabulary that we're going to search for in the corpus. Then I'm going to create a hash from that word list. And then my basic loop is loop over the records in the corpus. I'm going to then take that line. I'm going to parse it into words. Then I'm going to do a loop over the words in the record. And then if the word is found in the vocabulary, write that record to a file, say word.txt, where word would be ant, boy, car, and so on. So it's actually, the implementation was pretty simple. I was able to do this in about 70 lines of Perl. There's a few complications that I'm not showing. For example, the I/O buffering. We don't write a single record at a time. Instead, we'll accumulate results into buffers, write them out maybe every 10,000 or 100,000 or a million records. But it's actually very, very compact. So what would it look like here is implementing hashes. First thing I'm going to do is I'm going to create a hash. the keys are going to be the words that I'm looking for, the words in my vocabulary: ant, boy, car, dog, egg. The value that I assign to the hash is really arbitrary. Now the workflow is going to look like, read in that first line of the document. Now I'm going to go through each of the words. Is ant found in the hash? Is it one of the keys in the hash? In this case, it is. So I'm going to write out that record to ant.text. Is boy found in the hash? It is. So I'm going to write out the record to boy.text. XXX is not found in the hash. Dog is. YYY is not found in the hash, and so on. Basically, I read in that record one time. I parse it. I compare the words, so the words in that record to the hash to see if they exist. And it turns out the speed up was pretty dramatic. This was done using a single core and a Gordon compute node. The data was read from and written to the SSD. So for this benchmark, we did the search against Google 2-gram data for words starting with MO. So this was 319 million records. And I should add that the timings don't include the time to copy the Google Ngram data from the parallel file system to the SSDs and back. That was about a minute. So I'm showing timings here for different word lists and different numbers of words. The column that I labeled time, the third column, that's my implementation. So the column labeled grep is the original implementation, and these are in hours and minutes. So when we're looking at a modest number of words, say 100 words from a list of 10,000 words that the developers had provided me with, but my implementation is actually a little bit slower. We get a speed up of 0.72. When we scale up to doing a search for 1,000 words, so you'll see that the time is unchanged, practically unchanged, and this is to be expected because hash lookup that they don't scale with the size of the hash. They scale with order constant time. We see that the time is virtually unchanged, whereas as expected, the implementation using grep took about 10 times longer. Now we're looking at a 7.2x speed up. When we scale up to 10,000 words, in this case, I didn't actually do the full run using the grep. It would have just been too timely and expensive. But assuming that it continues to scale linearly with the number of words, we're now looking at about a 67x speed up. And then when we finally do the problem that they were really interested in, and that was to search for all of the words in Wiktionary, and in this case it was about 400,000 well-formed words that didn't contain numbers or special characters, we found that the time that now took about an hour 22. There's some overhead associated with the I/O and with the construction of the initial hash. We estimate though that the time to do this using grep would have been a little over 2,000 hours. Now we're looking at speed ups of about 1,500x. So it's a complete game changer for the developers. So I thought we were all done, and then there was one more wrinkle. The programmers at idea.org, they have background programming in Ruby and C++ and not Perl. I tried to convince them to use Perl. I love Perl. I've been using it for years, but I realized that Perl is a little bit of an older technology, and Ruby is much more popular now. So it gave me an opportunity to learn Ruby. Fortunately, this was a fairly short script, so it wasn't too difficult of a job. I re-implemented my solution in Ruby, and it was a little bit slower. It took about 20% longer, but we thought that was a small price to pay for giving the developers a tool that they can understand, that will be easier for them to manage and augment in the future. So my Perl solution for this problem took about an hour and 22 minutes. The Ruby solution was about an hour 41 minutes. So like I said, about a 20% performance hit, but I think it makes the developers much more efficient. So the one wrinkle with this solution is that we're generating large numbers of files all at once. So instead of searching for all of the records that contain a particular word and writing out that file, and then we can process it or do something with it, instead, with the hash-based approach, we're essentially generating one file for each for each word in a vocabulary. So the output we had was too large to store on the NFS file system. The large file counts will overwhelm Lustre. So what we did was we took advantage of Gordon's SSDs. We wrote these hundreds of thousands of files to the SSD. We then created an archive, which we moved to the parallel file system. Actually, to be more accurate, we generated the archive directly on Lustre by writing the data from the SSD into the tar file. And then what Wordflare developers can go back, they can extract files as needed. For example, you'd use the tar syntax to extract particular files from that archive. The one gotcha that we told them was, do not deflate this entire archive in Lustre in our Scratch directories. That would cause a lot of problems, suddenly writing 400,000 files in probably less than a minute. And if you are working in Lustre, delete your extracted files when they're no longer needed. What I really encourage them to do, though, was to take these files, copy them back to the SSD when they're doing their post-processing, and just delete when they're done. So in summary, we were able to get modest improvements to the Gibbs LDA++ code, about 1.5 to 2.2x speed up, depending on the number of topics being searched for. So even though this is a fairly modest improvement, it still has the potential to have a very large impact since the LDA algorithm is so heavily used. For their particular problem, I think it was a game changer. We gave them a better than 1,000x speed up in identifying n-gram records containing specific words. They had written their original allocations request asking for on the order of 1 million SUs. Their computing needs are now about on the order of thousands of SUs. And I should say, when I looked at the amount of data that they had to process, what they really needed was quite a bit more than the 1.5 million they had asked for. It would have probably been on the order of tens of millions. But what's nice, though, is that this is still an Exceed project. They still need Exceed resources, but it's more of a data problem than a compute problem, because they still have large volumes of data and large file counts on the order of 100,000 to 1 million. So with that, I'm going to wrap up, and I'm happy to take any questions.
Thank you, Bob. Do we have any questions for Bob?
Hi, Bob. This is Amit. I have a couple of questions. It's a very interesting and nice work. So I'm curious, why did you choose to write the files as individual files as results rather than just appending the entire thing into one big file, which would be grep, right?
Yeah, it was.
Okay.
So that was based on the workflow that the Wordflare developers had. They preferred to have a file for each.
I see.
For each word, and I think just the way they had written their other software is much more convenient for them to work that way. And of course, if you would be doing a grep on that file afterward, there would be a lot of work doing the grep.
It's only results, right? So it would just give you n number of lines where those results are going.
No. It's yes, but the results files are going to be very large. So we're not doing counts. We're actually writing out all of the lines that contain the word that we're searching for. So what's going to happen is if you're looking just at, say, just the 2-gram data, you're going to end up with a volume of data that's at least twice as large as the data that you started with. And as I showed, just for that one little subset of the n-gram data, 2 grams starting with MO, it was a third of a 300 million lines. So yeah, it's a lot of data. And you had a second question?
Yeah, the second is just curiosity. So you mentioned that the programmers were mostly C++ and Ruby, and I'm curious, they didn't attempt to do this in C++ itself, because I presume grep has a C library.
Yeah, they could have done that, but even if they did write it directly in C++, they would have still run into the same problem that I described earlier in the presentation, where each time they would have to go through the entire data file. So it would have been more efficient, and we would have probably seen the crossover point between a hash-based approach and the C++, and their grep approach, being pushed out to larger word counts, but they would have still had the same scaling problem.
Yeah, sure. Yeah. Well, nice work, Bob.
Bob?
Yes.
So is this running in parallel, or it is just running serially?
This I had running serially, but they could run this in parallel if they wanted to operate on different portions of the Google Ngram data in parallel. For example, you might want to run this for the first part of the 2-gram data, word starting with A, and then another instance for words starting with AC, and so on and so on. So there's a natural parallelism there, but what I did is purely serial.
So there is some efficiencies you can derive further, I guess. I mean,
Right.
you can split that data into multiple chunks, and you can use each process.
Yep, exactly. And in fact, Google already does that for you in the way that they break up the Ngram data. Because otherwise, you would go to their website and you would have to download I don't know, maybe it would be a 10 terabyte file. Right. Any more on that question?
Hi, yeah, this is Alan. How did they fold this data back then into the mobile app? Are they making queries against this out of the cloud, or how does this translate into their mobile app?
Well, that was the part I didn't really want to get into too much here because
okay.
No, that's okay. And the reason is it appears that the project has kind of fizzled. I don't know if it was a funding problem or a scale problem. Last I saw on the Wordflare website, it had just an icon that said coming 2014. So unfortunately, I can't answer how they would be doing this. But I should say though that the Wordflare app, it wouldn't have to operate on these many terabytes of data that I'm generating. They have a post-processing step that they would do, and it would be condensed down to something a little more manageable, which would simply indicate the strength of association between word pairs.
Okay. Thank you.
Oh, you're welcome.
This is Mona. Just a quick question. The mobile app portion of this project, was that something that ECSS was taking on, or is that something they're doing themselves?
That was something they were doing. We had no involvement at all in that.
Okay, thanks.
Yeah, so as I mentioned at the beginning, my involvement, the exceed involvement, was purely on this massive text processing problem. Then they were going to take it from there.
Bob, this is Amit from SDSC, a different Amit, so that he doesn't get credit for this question. Why are there more handsome women than beautiful men? I saw on this chart.
I have no idea. That was just an example that I randomly pulled up for. Yep. So no, I can't answer that one.
Okay, I was just kidding. Okay.
Okay, sorry for the background noise over here. They're doing some kind of landscaping outside. So if you're hearing that buzzing, that's on my end.
Well, are there any more questions for Bob? Well, thank you so much, Bob and Ritu, for really fascinating presentations, and thank you, everybody for coming and to our session today. We'll be posting these recordings to YouTube like we always do, and I imagine we'll be gathering slides from you, Bob and Ritu, Actually, if you send them to me, I'll make sure that Nancy gets them, and we'll go from there.
Thank you.
Thank you.
Thank you. Bye-bye.
Thank you.
Thanks.
Bye.
Bye-bye.